Okay, let's start. We are talking about orchestrating AI models in Kubernetes, specifically deploying Ollama as a native container runtime. So my name is Samuel Veloso. I work as a software engineer at Cast AI. I am in the security team, where we are building a product to find and fix vulnerabilities and anomalies in Kubernetes environments.
Yeah, and I'm Lucas. I work at Red Hat in the ROI Red Hat AI platform, and I'm also a Kubeflow contributor member.
So I work in security, but today I'm going to talk about AI, or more about Kubernetes, okay, and how Kubernetes works internally. So let's start. So if you have never used Ollama, if it's the first time you hear this tool, Ollama is a CLI tool to run models, AI models locally in a very simple way, okay? This is the GitHub repository of Ollama, and you can run the most famous model like DeepSeek, Llama, and any other AI models. And it's very popular. I don't know if you are aware, but the number of stars in the GitHub repository, in the Ollama GitHub repository, is 134K. It's even more than Kubernetes, so it's crazy, and only in the last year or year and a half. And why is that? I mean, the AI hype is real, and also I think it's because of the simplicity. Because if you want to run a model locally with Ollama, what you have to do is first you need to download and install the Ollama binary from the Ollama website. You need to start the Ollama server in the background, and then you download your model with Ollama pool. For example, in this case, it's the Llama 3 8 billion parameters model. And to use the model, you only need just to execute Ollama run and the name of the model you recently pulled, and that's it. Then you can start talking with your LLM, as you are doing with ChatGPT, but locally. You can also consume the APIs, for example, and integrate Copilot or any other tool with the model locally, so you don't need to send your data to an external or to a third-party server. So, and if this could sound familiar to you, because the Ollama pool and Ollama run is very similar to Docker, so the UX is pretty much the same. So Ollama is to models what Docker is to containers. It's a tool that simplifies the deployment of models. So when we were experimenting with Ollama, the one question that came to our mind was, okay, this is for local, but what happens with Kubernetes? How can we run Ollama in Kubernetes? So the first option is there is a Helm chart that you can use. It works pretty well, and it's really well maintained. So it's a very valid option. But we were thinking about, can we do it in a more Kubernetes native way? Can we use a deployment? What happens if we put the model that we are pulling locally, but in the deployment image, as we are doing with any other Kubernetes application? Okay, and it's possible. We need to set in our deployment this runtime class name, okay, that we have in there. And by default, we don't need to put this runtime class name, because by default, we only create containers. But if we want to create other things, or we want to delegate the creation of our deployment or containers to the container runtime, or we want to use a custom container runtime, we can use the runtime class names, okay? This idea is not new. It was introduced in Kubernetes 1.20, so a while back ago. And actually, it's the way that, for example, Containerd, one of the most famous container runtimes, it's the way it implements the runc. So when Containerd needs to create a container, it talks to runc by using the Containerd sim runc v2. Other projects, for example, Kata Container and gVisor, do the same or are also using the runtime class to do a similar thing. But in this case, they do not create containers. They create isolated sandboxes or virtual machines. So when the Kata Container or gVisor runtimes wants to create or receives the request to create a virtual machine or a task, it will be a virtual machine. It's not going to be a container. And the same, for example, for the WebAssembly sims, for WebAssembly workloads. So we are going to explore how can we do this with Ollama, okay? And how can we use this custom runtime class to implement a custom sim to deploy and expose models in Kubernetes. So the first question to do this is, how does Kubernetes work? Okay, it's a hard question, a very wide topic. So we are going to be a bit simplistic in here. But basically, we are interested in what happens when we create a deployment or how the containers of that deployment are created on every node. So in our case, we have this deployment with a custom runtime class name. So what happens in Kubernetes when we do this? When we do this, when we apply the kubectl, when we run the kubectl apply -f, so the control plane, if you are Kubernetes experts, you know that it's more than this. In the control plane, we also have the scheduler, the controller manager, we have more parts. But at the end of the day, the API server will receive the request and will store in etcd the pod, okay, that it needs to be created. Kubelet, on the other side, it's installed on every node, and it's continuously watching pod changes in etcd. It's watching the API server, and when there is a new pod, it's going to call this sync pod function. You have the entire definition in this URL that you can check later. We have the slides in the sketch. So this sync pod, what it's going to do is Kubelet is going to request the CRI runtime to create the containers for us. So let's see, the sync pod implementation is something like this. It does, as you can see, many things. We are going to review now what are these different steps, so don't worry about the comments. Basically, what we need to pay attention to is the body of the function, okay? So we have the sync pod. Sync pod is calling the CRI API because we have two main container runtimes. We have Cryo, or we have Containerd for GKE, EKS, all the Kubernetes cloud flavors, also Kind for development, and in OpenShift environments, we have Cryo. So we have an abstraction, so Kubelet work in the same way with any container runtime. And this is like this because we have the container runtime interface. These are some of the endpoints that are defined. You have the full specification in here. You can go and check out. And we have two main services. We have the runtime service and we have the image service. Runtime service is used to create pod sandboxes and containers. And the image service, the same to interact with the different, to manage the images in a node. So let's review the run pod sandbox API first, because it's the first API to be called when we need to create a container. This API will bootstrap the cgroup, namespaces, and network for all containers in the same pod. And that sandbox will be initialized with the post container. It's just a dummy container, a for loop running, and it will be the first container of our sandbox. The way it works is, okay, Kubelet is watching the pods from the API, and then there is a new pod, and it's going to create that pod. So it will call the run pod sandbox request. It will send this request to the CRI runtime. The CRI runtime first will get the sandbox runtime. Okay, this is what we specify in the runtime class name. So we are going to get the runtime sim that will handle the creation of this request. So by default, it's runc in Containerd. In our case, it's going to be Ollama sim. That it's a component that we are building for this. The next step is setting up the pod. It's going to call the CNI. It's a different interface. It's the container network interface. It will set up the network for us. It depends on the network provider you are using, Cilium, the cloud CNI, or whatever. And finally, it's going to start the sandbox. The pod sandbox, it's going to create one container, the post container, with this create task request. So the runtime sim will create this container for us, or for the sandbox. It will return the process ID, the PID, and finally, it will return also the sandbox ID to the kubelet. So next step, okay, we have the sandbox, it is ready, and now we need to attach or add containers to this sandbox, the actual container, or in our case, the model that we want to expose. And this is what the Create Container API is for. So it will attach the container or multiple containers to the pod sandbox. So now we have the post container and also our containers. And it works in a very similar way. In this case, the kubelet first calls the pull image request to the CRI runtime. So the CRI runtime, for example, containerd is going to pull the image that we specify. It will return the image reference, and then it will, with the create container and start container request, it will finally talk with the runtime sim, Ollama sim in our case, with these two different calls with create task request and start request to create the container that will be in the sandbox. Finally, it will return, if everything goes fine, it will return an ACK. And so the requirements that we have to build our container or custom runtime, container runtime or our sim is, okay, we need to pull the models with an OCI format, and then we need to build a sim compatible with containerd. The first thing is, okay, because we are putting a model in the deployment image, and that image needs to be OCI compatible. So we cannot put the image directly from the Ollama registry because it's not compatible with the OCI format. So the question is, how do we convert models from the Ollama registry to OCI format? We can use this tool, okay? It's a tool from the GPU stack. It's called gguf Packer Go, and it converts gguf models to OCI images. If you are not familiar with the gguf format, it was developed by Georgy Yerganov. He's the developer of the main contributor of Llama CPP, and it's a binary format that simplifies, or it's an optimized way to store and share AI models. In Hugging Face, we have more than 90K models with this gguf format, so most of the models are available in this format. And how does this tool work, this gguf Packer Go tool? It works like a Docker build, okay? But we have a custom builder, so we need to put our gguf model inside. In this case, it is in the add instruction. We are pulling the model from Hugging Face. In this case, it's the QN2 model. And it will, then we need to call this Docker build just with the name of the image that we want to push to our Docker registry, as we do with our application, with our Kubernetes services. And that's it. The image will be available in our registry, and it can be put into the deployment, in the image deployment. With this, when the CRI runtime, when containerd receives the pull image action, it will pull the image into the node, and it will be available for the containers to mount this image or to use this image, as we are going to see now. So, okay, we have solved the problem of building the models in a format compatible with containerd or with OCI. Now we are going to see how to build this sim, what we need to create a custom sim, in this case for Ollama, but it can, the idea is the same for any other. Okay, what we need to do is, this is for containerd, okay? For Cryo, it's the same idea, but a bit different. So in the talk, we are only going to work with containerd. We need to set the custom runtime as a plugin. Okay, containerd allows to define as many runtimes as we want, and we need to use this runtime type and register our containerd sim. We need to copy the sim binary to the Kubernetes node. I'm going to explain in the next slide how we build and how to write this binary. Okay, but for now, we need to copy the sim binary into the Kubernetes node, because containerd will execute this binary every time we create a pod sandbox. And the last step is we need to create this runtime class object in Kubernetes to map the binary and the runtime class name that we will specify in the deployments. So the binary. Okay, this is the important part, how we code this sim. We can use, if we are using Go, we can use the containerd library because containerd is written in Go. So we need to call this new sim manager, and we register our sim with the same name as we have in the runtime type in the containerd configuration. So it has to be the same. And then we need these 3 files, only 3 files. Okay, we have this, the manager, and then we need to define the plugin.go and the service.go. The service.go is the important part because it needs to implement this huge interface, the TTRPC task interface defined by containerd. And yeah, it's quite complex. I'm not going to get into the details of all the different methods that needs to be implemented. We used the containerd sim run cv2 as a reference because it is available. It's what containerd is doing to create the containers. In our case, our model is also going to be a container. So it's easy and it's the simple way to write a custom sim, a containerd sim. So and actually the most important method that we need to implement is this create method. As you can see, we have the create task request. It's the information that the sim receives when a task is going to be created. A task is usually a container in the runc context, or in a context is the container model. Okay, and we have in this request we have more parameters, but these are the 3 most important parameters. It's the ID, the bundle, and the rootfs. The bundle is a string to a path in our host that stores the information of the container that needs to be created by the sim. We have several files. The most important one is the config.json file that we see in there. Okay, this config.json is just the declarative definition of the container. So what we put inside the pod spec is translated by containerd and stored in this container.json file with all the information about our process container. For example, the user that is running the container, or for example, the mounts. Okay, the mounts is relevant. You will see in the next slide why, but we have all the mounts that the container will be available. So, because what we are going to do is with our sim is we are going to mutate this config.json information that we have in here. For example, we are going to add 1 more mount to the list of mounts. We are going to mount Ollama from the host into the container. This is the first part, and Ollama now will be available in the container. The first part is we need to load our model, but with Ollama doesn't support to directly read the gGUF model. So what we need to do is we need to put this from the name of the model inside this model file name. So this is what we are doing with this piece of code. We are just creating a temporary file, the model file name with the name of the model, the gGUF model that we want to run, and we are mounting this model file also into the container. And finally, we need to initialize the container to expose and to serve the model. And we do this by just running Ollama serve and now creating the model from this model file that we have mounted in the previous step. So that's it. With that, we can just create our deployment, our model with the custom runtime class, setting in this case Ollama sim. It will be our runtime class name. And then the containers will be our model. We want to create this QN2 model. It will be exposed in the port 8080. The model name will be QN2, and the model path, we need to specify where this model is, because we can have, for example, several models in the same image, so we need to specify what model we want to load. And that's it. You will see then in the demo how all this works. And for now, Lucas will talk about how to integrate this with Kubeflow.
Yeah, thank you, Samu. How's everyone? Okay, for the next 10 minutes, we are going to talk about hey, now we've just had so much fun just trying to get Ollama in Kubernetes. Why did we use Ollama rather than, I don't know, gVisor for VLM or something like that? because it was just so much fun trying to do that. So we were gonna try to do the same for the UI. After we finished our development, we thought, okay, how can we translate that into something that the community can use? So we look at Kubeflow, which I don't know if you guys are aware, it's just part of the CNCF Foundation. It's the MLOps platform that right now it's used for several components AI related. Kubeflow makes just like MLOps workflows easier for users, and you can install that in any Kubernetes cluster. And Kubeflow is based on several components installed inside a central dashboard. You are covering most of the MLOps world. So with Kubeflow, you install different components such as notebooks, pipelines, a central dashboard to get everything all together. KT for parameter, hyperparameter tuning, Kserve, which is basically a service for inference. And you can see much of the workflow, the MLOps that we have right there. Right now, we even have model registry, which is generally available since yesterday, in which we released the 1.10 version. And we thought, okay, this is nice, and there's so many features right now. But can we make Ollama part of that as a model catalog? Yesterday, they announced that they have a backlog for the 1.11 release. You get a model catalog inside, or like in the next following release inside this platform. So will it be nice just to try to do a POC and get this same service working in a Kubernetes cluster? We thought about that 2 weeks ago, and we were like, hey, do we have time to just display something like that? And we were like, okay, let's do it. Let's just try to vibe code through everything and get something working. And that's where we started to use the model architecture that it's currently available in model registry. Model architecture is just one new way of developing Kubeflow components. It's just basically, there's no rocket science here. It's just like a front-end and a back-end, front-end in React, back-end in Golang, but it's just based on microservices. So there's a cool set of features that makes the development experience really, really nice. So we are gonna just try to get those things to make application available in Kubeflow in no time. So the most important of these architectures is that it enables contributions from other projects to Kubeflow. So we just thought, okay, let's just try to do that. So that's what we did. Like we got a nice UI in no time to have it displayed here. So how could we do this in no time? It's because model architecture serves like different environments to make the development workflow really easy. We have a standalone mocked mode, then we get the standalone mode, and then integrated, which are the parts of the demo. Let's just switch to the project itself. This is a VS Code instance with the containers in Ollama. Here's everything that Samu has explained, everything about that. So let's just trigger the first development environment. This is what we call like the standalone mode with mock components. This means that we are getting the feature as a standalone, like outside Kubeflow, but that makes everyone can contribute in no time. I just like get this makefile command, and now hopefully I got here the application enabled. Let's just do something because I think I got it in. Let's just rerun it again, and with that, let's just reload. With that, we have the UI itself. As you can see right now, there's a model catalog with different models right here. We got like Quen, which is the one that we've been talking about, and some others. And here we can see the model catalog with the description and everything else, version. I'm not sure if it's Like, let me just zoom in a little bit more. And here there's a nice chat display in which you can talk with the model. Problem is that this is just like if I do a hello world or something like that, you see this is a mock response. Why? Because this is just for development. So here's when where we craft all the UI. That makes us like, for example, if we are a front-end contributor and we just want to change this, the available models into Ollama models, we can get to the actual place and put something like this. And in no time, it will be changed into the UI. So you don't need to know about Kubernetes or anything else. Everything is through a Swagger specification between the backend and the frontend. So people that knows Golang can contribute in the part of the backend, and people that only knows frontend can contribute into that. That's already there in the model registry, and we're expanding that into other places. This is nice, but like this is not going anywhere, and we are not doing anything with the POC. So let's just change to the next environment, which is the standalone version, but with a cluster itself. So right here we have a cluster working. This cluster is just the one that Samu has been explaining right here. Here we have the cluster with the configuration around like all the SIMD changes that we've been doing, and the Quen model deployed. As you can see here, we have the deployment with the image itself, the image that we've created with that. And a service that it's been exposed somewhere. We have this script, which is the one that we are using for developing in cluster. This will create you a kind cluster the way that it's displayed in the repository. And then it will create a namespace. This is like the default one called Qflow, and it will deploy that model right there. And then it's just like deploying every other file that it's needed to do the deployment of UI. Everything's done right there. Let me check if we are in the right. Yeah, we are in the right cluster, which is the kind of Ollama SIM. So I'll just need to expose this service, and we'll see this cool little demo right here with pretty much everything. This is a standalone version. We'll see what's the difference between the standalone and the other one. As we can see, the UI has changed right now. So let me go back to the development one sec. Here I just have it with the a component library standalone version, which is like this, is Patternfly. And we have a wrapper to get like the look and feel of Qflow, so everyone can contribute, and it will match wherever we have right now in Qflow. And it's basically doing that same thing. Here, this is a Kubernetes cluster, and as we can see in the Qflow namespace, we have the application deployed, and then the model itself. Let's just check the model. Here are the logs. So let's see how we can interact with that. Right now, the set of features that have here is just like we are reading all the catalog model from a config map that will change in the future, in which we can pull those models through an API. But so far we have in the metadata the service in which the model is exposed. So for that, we have enabled the chat interface right here. If we go to another model that it's not deployed in the cluster, you have this, which is not implemented yet. So if anyone wants to contribute to that, feel free. And here in the chat model, if I just say, for example, why is kubecon, it will just send the request. As you can see in the chat, it's just doing all these, like the inference is just enabling the model, like getting the arg, the name, the parameters and everything through the runtime is just starting up the model and doing the inference right here. So basically, what it's doing behind the scenes is a Golang service. It's just like talking through the service, getting getting there, and posting as Ollama has the OpenAI/Ollama service exposed, in which you have the generate endpoint to talk to your models. As it's the same, we can implement several different, if your model is multimodal, you can get the other endpoints to just interact with that model and craft a UI with that. So that's great. Now we have everything working, and we've just like touched the cluster in that second phase. Next phase is Qflow. integration. Problem with Kubeflow integration is that Kubeflow is a really great project, but right now it's very cumbersome to install. It requires like 16 gigabytes RAM of GPU, CPU cores, and that makes like some contributors like it's just not great to be a newcomer and just make sure you have a contributor. So that next step is just like this modular architecture has everything needed to deploy everything into Kubeflow. With that, we have pretty much everything in this manifest to make it compatible with the platform. As you can see here, we have the authorization policy, destination rules, network policies, and everything that it's Istio related that is needed for Kubeflow. Let's just change the runtime, like the context of Kubeflow right here. And let's just see that in action. So I have a cluster running right now. I think I'm connected, yeah. With Kubeflow enabled right here. Let's just get there. I'll just get here. Oh, this is a spoiler. One sec. This is a cluster running with Kubeflow itself. This is a Kubeflow interface. This one is just a mock, like the other one that I saw you. It's just like to make it the most appealing and the most similar to that. Like here are all the components with Kubeflow. We are deploying everything that it's available to the in the interface to make it work right here. As you can see, well, here are the namespaces. Let's just go to the Kubeflow one. Here are all the pods that we have in Kubeflow, which are all the components that are running. And as you can see, we have the Ollama UI up and running right here. So as well as the model registry component, that is a new one, we made in less than a week a new Kubeflow component based on Ollama. So here, as you can see, we have the model, and we can do the same thing, and everything is right away and available. This is only a POC, but this is like just to show you guys how we had fun to just implement some idea and make it available for something as a CSCF project in no time. So that's all. Thank you very much. And yeah, I hope you all have a great evening. Thanks.